Yeah, so I was actually going to take a poll to see how many people would actually end up on the last day of Spark Summit at arguably one of the last times in this weather condition. And I had a poll going, and we have far surpassed the number of people that I thought was actually going to be here. So we can all give ourselves a round of applause for that. All right, yeah. So I'm John. I work for a company called DNV GL. We use Databricks. Databricks has got me into this kind of world and really introduced me to Spark and the possibilities of Spark. And so thanks to them for giving me an opportunity to come up here and talk about this real quick. My presentation is going to be probably a little bit different than a lot of the ones you've seen today. I'm definitely not a software developer per se. As a data scientist, I guess my background is definitely more in mathematics. So the mechanics of how Spark works is not something I'm going to focus on, nor is it something I profess to be very good at. But I will tell you really cool stuff that I've been able to apply Spark to, and hopefully you find some value in that. So first of all, yep, this is me. I'm a consultant for a group at DNV GL called Policy Advisory and Research. A lot of our clients are utility companies. A lot of our clients are regulators, governments, that sort of thing. So to try to put it in context, we do a lot of offline analysis. Not a whole lot of streaming or online predictions, but a lot of offline analysis, but with very large data sets. We have a lot of challenging tasks where we have to deal with extraordinarily large data sets, and we have to do it in a relatively quick turnaround. Yeah, my background, like I said, is a little bit more mathematical than programming per se, but my kind of love obsession is with forecasting, so there's a overlap there. Okay, so DNV GL. Raise your hand if you've actually ever heard of DNV GL, besides Trey and John. Yeah, exactly. DNV, because it's weird, right? Our clients, we're a consulting company. We're actually a very large consulting company with 16,000 people based in Europe, and we definitely don't typically operate in this space, but we do have a lot of overlap. We're very technology driven. And it stands for, I'll try to say it, it stands for Det Nordske Veritas Germanischer Lloyd. Which is actually, there's like 3 languages in there. But the first 3 letters is the Northern Truth in Norwegian. But it's a really cool company. You should check it out if you've never heard about it. And at least I don't have to, people actually get confused that I work for the DMV, the Department of Motor Vehicles, which I do not. But I'm sure there's some application of Spark there too. Okay, so I want to talk about 3 things. So I want to talk about the data scales, and DGP up there stands for data generating process. The reason I got interested in Spark over the last 3 years is because I have actually seen an explosion in data sizes from my clients. And I've been trying to deal with it, and we've tried a few things, and Databricks has really helped us try to tackle some of these issues. And then I'll just go through 2 applications real quick, and this is how we're actually using Spark as is. And then next steps. So DNV GL, just really quickly, this is what we do. We're kind of a very diversified company. We do a lot of different things. We started off as a certification society. So we'd actually, in Norway, we would write these standards for ships and then certify these ships to say, like, can you traverse the ocean? So kind of a weird background. That was in the 1800s. And we've just grown and grown and grown and grown. And we've bought up different little subsidiaries too. So this is the kind of makeup of our company real quick. I work in the energy industry. My entire focus is on energy. But I just want to say it's a very diverse environment that we work in. Okay, so I like to use the term energy data science. Data science to me means a very broad knowledge of techniques and approaches. But when you apply to a certain domain, there's some nuances that you get out of that domain. So I like to apply data science to the energy domain in particular. So the data generating process, if you have a background in statistics, you might hear that phrase before. It's like, really, what is generating the observed data that you have? And so for me, that typically means historical time series of electricity usage data, right? So how much electricity is this building drawing right now, every hour for the last 10 years? That's a typical time series that I deal with. And then when you have that for all the buildings in Boston, say, and all of a sudden you have a blizzard, what's the impact on the electricity consumption? Well, probably goes up because everybody's inside. Those are the sorts of things that I have to think about and deal with. So one of the major data sets I deal with is historical metering data. And then the other major type of data is weather data. We also have to deal with economic data, financial data, all sorts of different information. But just, just to highlight metering data, this is where all the attention and excitement really is, because we have smart meters. I live in California right now. Yeah, I was born and raised here, but I live in California in San Francisco. And in California, I don't know if you knew this or not, in California, almost every single home in California has a smart meter on it. And what that means is that it's recording hourly usage. The population of California is somewhere around 38 million people. So we've only had 3 years since the majority of the population has had smart meters, but as that keeps going, it's just going to get larger and larger and larger because it's tracking historical data. Some of these data are being recorded at 60 minutes intervals, some are at 15 minutes, some are at the seconds. It's a very large data set, and it's much different than what historically has been going on for this industry. We typically deal with monthly billing data. So literally someone goes to the house and records how much electricity you used every month. 12 observations every year per person. Not that much data. Now we have 8,760 observations if it's hourly, right? Those sorts of data sets we're dealing with. So just a quick graphic of what it used to, this is old school. This is what it used to look like, right? Where some power plant generates electricity, it goes through some high voltage power lines, transmission and distribution, and it ends up in your home. And now we've got things like wind farms and PV on top. So we've got a changing landscape. But what is that actually changing into? This is what it's changing into. So the rise of the smart grid. So I'm sure everyone here has heard of IoT and all that sort of thing. This is a direct application of IoT. This is actually happening, where there are actually devices, even on a single structure, there's meters all over the household, for the solar panels, to the electric car charging station, to the storage batteries that are coming any day now. This is the future, and to get us to a place where this is real will require some serious analytics, and we're going to have to deal with very large data sets. Okay, so this is fake data. I just made this up to kind of make a graphical representation of some of the stuff I have to deal with. So on that z-axis is the number of meters, right? So number of buildings, if you think about it. On the x-axis is geography. So if I'm dealing with an entire state, an entire town, an entire country in some examples. And frequency, how frequent is the meter capturing that information? Is it every 15 seconds? Is it every second? We've found, I tried to make this, it's fake, I made it up, but I tried to make this a little bit nonlinear, because this is actually what we found, is that when you try to scale in these dimensions, it's totally not linear. And it's actually really difficult to deal with, which is why Spark has been the obvious solution. Okay, so why? Why has Spark been the obvious solution? What are we doing in terms of analytics? So I use the term primary modeling unit quite a bit because it's abstract enough to just realize that whatever that is, that's the level that you're trying to forecast or model at or aggregate. That's your bottom level, your primary modeling unit. And there's various forms that could take. So maybe you're coming up with a model for every hour of the day. Maybe you're coming up with a daily model or a monthly model. Or what if you're doing that and you're combining with cross-sectional information, right? So for example, a utility has different rates, so everybody's on a different rate. They get charged different fees to use electricity. And hybrid is some combination of the two. And the example I'll show you is a little bit of a hybrid. So what Databricks has done is enabled me to kind of get in there, figure out how a lot of this stuff works really quickly, and kind of scale that out to other applications, right? So I'm able to get in there and play around with the models that I know how to make on a local native system or an on-prem system and do it in the cloud really quickly. But the real thing I want to talk about with this, a lot of this is on, is Spark 2.0. And so my primary weapon of choice is R and Python. Those are the two things I know the best, and I like that. What I haven't been able to do in Spark up until 2.0 has been this embarrassingly parallel problem, where I have all these different models that I want to get, millions and millions of models, and I haven't been able to do it very effectively. So now, as you've probably heard from a lot of the talks today, we have UDFs and the capability to do partition-based modeling as opposed to, or rather, group-based modeling. And 2.1 is just, I just put that up there because I wanted to say, we've written tons of packages that we've been trying to figure out how to get it onto a Spark cluster, and 2.1 has had the spark.add file function added, which has helped us quite a bit. So it's only really until Spark 2.2 came out that we were able to do a lot of what we wanted to do with Spark. All right, I want to talk about two applications that I've used Spark for. One is called the Princeton Scorekeeping method. This goes way back, way back, like 30 or 40, I think, years. I have a colleague who was my boss's 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 boss who came up with it with her PhD dissertation. And all it really is, it's called Prism. The point of this is to decompose a building's energy usage into its baseload components and its weather-sensitive components. Right, so it's really cold outside, we use a lot of electricity. When it's really hot outside, we use a lot of electricity. It's nonlinear, but there are different components. And then there's also some baseload that's just always on, like the lights are always on. This analytical approach tries to get at that, tries to quantify what the actual sensitivity to the weather is. And like I said, it's been around for a long time. It's not something I came up with, but being able to do it for millions and millions and millions of models is very interesting to us, and we do this for our clients. Okay, so it involves a few things. You're coming up with a model for every site for every year. You're searching over a grid of possible cooling and heating reference temperatures. Everyone sets their thermostat differently. Some people put it at 65 degrees, some put it at 70. If you're in California, in Northern California, you don't care. You don't even know where your thermostat is in the house because you just don't care. And it comes from a rich history of actual structural engineering principles of buildings, like the building envelope. It's a very involved algorithm, but it actually surmounts to a relatively simple approach, simple equation. Promise is the only math I have to show. It kind of bugs me when people throw out math without explaining what it is, but this is actually pretty simple. In that equation, on the left, you've got energy usage at time t is a function of, it's a linear function, it's a very simple linear function of heating and cooling. There's some heating going on, there's some cooling going on, and that tau h and tau c are the threshold temperatures. You're actually saying, at 65 degrees, what is the effect? At 70 degrees, what is the effect? And you search over all of these possible candidate reference temperatures for every site, for every year. We're literally talking about millions and millions and millions of models. And if you're kind of familiar with some of this is really just, these are two basis functions, cooling and heating. Right, so when we do this, what does it look like? This is a graphical representation of what that kind of looks like. This is actually from some other research I've done, but this is the estimated cooling and heating trend for New England. This is historical data of New England. This is real data. Electricity usage is on the y-axis and temperature is on the x-axis. So like I said, when it's really hot out, when it's 100 degrees, we're using a ton of electricity. When it's really cold out, we're using not as much, but still a lot of electricity. So those two slopes, that's what you're going after. They're really just two splines. But we're trying to characterize this for every single household that we're trying to do this for. It's a very complex thing. Spark should be able to help us. This is an embarrassingly parallel problem. I should be able to do this. It's a simple algorithm. I should be able to do it over and over and over again until I come up with an optimal solution. So I do have some notebooks to show, but we don't, I think a lot of people here are familiar with what that code's going to look like. But here's an example of how I've done it with Spark 2.0. This is a really simple example using gapply, right? So grouped partition apply. And if you know R, you probably know lapply, or the whole family of apply functions, which this is modeled after. So this has really helped me to quickly do this and to quickly figure this out without going into too much of the mechanics under the hood. And I really like that. I really appreciate that. So here's just some simple code of how we've done it, and it works incredibly well. We've gone from, I had one thing that I was doing on a legacy platform that took 24 hours. It took 7 minutes in Spark. Like it took 24 hours to 7 minutes. That's incredible. That enables us to do a lot more with the time that we have. And the only point of me really putting this up there is to kind of show, here's how you start to develop these sorts of models. If you look at that line that just says LM, I can't really point to, oh, maybe I can point to it. No, I can't point to it. That's essentially what we're doing. We want to be able to change that model in various different ways. We want to do a bunch of different algorithms onto that. Okay, so what's the result? Well, the cool thing about SparkR, one of the cool things about SparkR is that, especially in the Databricks environment, once you've done the necessary computations that make sense at scale, you can bring the results into a local R session and actually just kind of look at it and analyze it with things that are a little bit more familiar to you. So that's what our kind of best practice is to do right now. This is an example of this. This is actually the resulting, if you're familiar with the titer or dplyr package, this is kind of just doing a little bit of data transformation once it's been local and displaying some of the results. And I have some graphs that'll help explain what that is. So this is a really cool graph. I really like this graph. And why do I like this graph? Because it tells me quite a bit. The red is the final chosen temperature over an entire population of people for how they react to how their electricity responds to temperature. So that x-axis is really temperature. It's not very well depicted. But the cooling is off to the right and the heating is off to the left. So basically this is saying at 60 degrees, that probability distribution right there, the majority of it's arguably around 60, maybe 58. Most people, that's their temperature. That's the temperature where they actually start reacting. And we did this in Spark. So this is for a residential population. You can kind of get a feel for how spread out it is. Lots of households, lots of people are much different. This is a commercial and industrial population. You got a lot of corner solutions, right? You got a ton of probability mass at the corners of your grid that you're searching. And that actually tells me a lot about commercial and industrial versus residential. Commercial industrial is very stable. Like this building is a commercial industrial place. It's on all the time, especially if there's a conference that's there. So these are the sorts of things that we've taken out of our legacy platform and really started to explore with Spark. Okay, so that was one application. And it's kind of an obvious, embarrassingly parallel application. The next one isn't so old. It's actually very new and novel. And my company, me and a few other people have come up with this approach to doing this. I just want to take 1 second to explain what this is. The biggest thing coming right now in the electricity industry and the energy industry is something called distributed energy resources. And that's a catch-all for things like electric vehicles, battery storage, solar panels, energy efficiency, demand response. All of those things that I just mentioned are going to affect the time of day that we use energy. They may or may not affect the overall quantity over the span of a year, but they're going to affect when we use energy. So one example of this is electric vehicles. So this is the actual electricity usage of just an electric vehicle charging station, right? This is real data for what it's worth from a client I have in Virginia. The blue line is the average, what we call load profile, right? It's an average shape of their electricity usage based on that person being subjected to a very specific electric vehicle rate. So in the middle of the night, it's really inexpensive to charge your car. They want to do that so that everybody who has an electric car, when they come home from work, if they plug it in right when they come home from work, it's going to cause a huge shift. If everybody did that, the way that we've structured our grid would not be able to deal with that peak. Typically, the peak is when it's really hot out in the middle of the day. So we've designed our electricity grid to accommodate that. If everyone got an electric vehicle, we'd be screwed because we wouldn't be able to deal with that. We wouldn't know how to deal with it. So utilities and regulators and governments are trying to figure this out. They're trying to be like, oh man, all this stuff's coming. How is it going to affect the way we act? Well, here's an example. Just really quickly, that black line is a control group. So that's what normal people who aren't subjected to this rate, that's their behavior. You can clearly see they come home, on average they start coming home and their electricity goes up. And then they go to work and it's not there. But the blue line has shifted. Now there's this high peak in the middle of the night. And electric vehicles are getting much smarter. You can actually just schedule when that happens, right? That's one example. Here's another quick example. And just flipping a little bit, that's an example of load shifting, where the quantity doesn't change too much, but the time of day does, right? The quantity, the overall consumption is, you still have to charge your car. It's still going to be the same amount. This is an example of just a reduction. It's called demand response. If you're not familiar with it, it's a program that a lot of utilities have where they can control your air conditioning at times of peak. At times of an emergency, they can kind of control, you opt into it and you say like, yes, it's okay to shut down my air conditioner at times of emergency, and they'll pay that person to do it. So you can see here, this is again real data that I aggregated over a utility in California, where you can see like, in the middle of the day there was an event called and they just reduced their energy demand. The point of all this is that this is affecting the hourly profiles, the hourly load shapes. Very complex systems of things are going on that we need to be able to manage. All right, so I did, this is a proof of concept I did last year for it was a forecasting conference. But basically I took a ton of people's actual AMI data from Canada. I took all of their AMI data. AMI stands for Advanced Metering Infrastructure in this context. So it's smart meter data, hourly electricity usage data, right? I only took the people that had the best quality data, so whatever the summation of 1, 2, 3, 4, 10,000, 4,000, 1,000, 9,000, I think it's like 22 or 23, 24,000, something like that. That's how many people I'm modeling. That's how many households I have. So how do you account for a bottom-up thing at the top level? So when I say bottom-up thing, I mean not everybody has an electric vehicle, but some of them do. Not everybody is going to be subjected to a demand response program, but some of them do. You can see how it actually needs to be modeled at the site level, not at the aggregate level. So we need to bucket people. We can't do that for everybody right now. You can't figure out the best model, best approach, best technique for every single household. So what do? And this is a classic case when clustering helps us out quite a bit. This is really simple. This isn't really complex. I just did k-means. I had two features. I had their peak demand, so the one value where they peak out at, and then their annual usage, so the aggregated values over the entire year. Those two dimensions kind of describe you. They say you might have a really high peak, but like a low usage. So maybe once in a while you'll jump up there. Or maybe you'll have a lot of usage over the year and it's very constant at the same peak, and that peak is very low. This is, like I said, this is very simple proof of concept. I just used these two features to kind of try to bucket people and see if it'll work, right? And this was kind of the results. I did it in MLlib really quickly. Since then, we've actually gone over to spectral clustering, which works a little bit better. And then once we've got these clusters figured out, right? And let's move on a little bit. I want to see, like, are they different? Did my clustering technique actually work? What was the point of doing that? Did that actually work? And so right here, we've got those four clusters with their electricity demand plotted against temperature. And to be honest with you, I don't see a whole lot of difference. I don't see a whole lot of difference in their magnitude. I think the shape is relatively the same, give or take. You got some outliers in the middle there, right? But they're kind of the same. And I kind of got worried. I'm like, oh man, maybe this didn't work too well. What am I going to do? In reality, it worked pretty well. So this is the fitted, this is obviously a surface that's fitted to temperature and relative humidity. So I took it a step further and I plotted it with relative humidity too. On the left, you obviously see cluster 1, and on the right, you see cluster 4. Those look significantly different to me. I think their reactions to the combination of temperature and relative humidity does look different. And again, this was just a first pass at doing a k-means simple kind of clustering. And you can already see significant differences between these clusters. The point is, we actually, at least kind of closely, identified differences in households without even controlling for that. And I'm still operating at the household level, or the structure level, which is very important. Once I'm at that level, like I said, just flipping back real quick, I had 4 clusters. Those are the sizes, and I just picked some colors. 4 clusters. You can come up with forecasts. You can come up with whatever model you want, whatever machine learning model you want to come up with a forecasting approach to predict that cluster's demand. And that's what I did. I really like semi-parametric regression. It's something I'm very familiar with, so I often just go to that as my default in the beginning. So that's what I did. That's what this is. Those 4 lines up there are a week out forecast of electricity demand for 4 clusters. Right? And you can see they're kind of different, but even here you can kind of see it's just kind of like 1, 2, 3, 4, like high, not so high, low, really low. Not a whole lot of difference going on there. What can you do with this? The scale of this is at the household level. Like your household and my household might be in cluster 2, and his household might be in cluster 3. But I'm treating them as the same for right now. But it's still at the same scale as a household. Well, guess what? I can simulate, at that level, I can simulate the impact of various technologies on that household, on that structure. I can say, hey, what if you got a solar panel? What if you got, so at the bottom here you'll see PV production and storage. That's the set of simulations that I did. And I said, hey, if you got a solar panel and storage, what is the combination? You can feed your forecasts into simulations such as this, and the output is an adjusted forecast. It's an augmented forecast that controls for the presence of distributed energy resources at the household level. And once you get that, and if you know that 10% of the population have a solar panel, and 90% have not a solar panel, and some of them have an electric vehicle, you can aggregate up and come up with an aggregate forecast for a town, a city, a state, that controls for the presence of various scenarios with distributed energy resources. And I did all this in Spark, which is really cool, and I think Spark is one of the only things that has made this actually possible, that I'm able to deal with this size data, and even just do a simple k-means on it and then move it forward. So take-home message, this is good. I timed this out really well. I got like 5.5 minutes left, so I really hate when people just keep talking and talking and talking. At a high level, what have I done? So Spark 2.0 is really with two, like I said. Like I really like R and Python, R in particular. And 2 has really made it easy for me, someone like me, to use Spark in a way that I can apply it to other things in life. And 2 and 2.1 has made that possible. Databricks, I gotta give a shout out to Databricks. I mean, they enabled me to learn this stuff really quickly. Their platform is really good when it comes to learning the mechanics of this stuff. And they enabled me to do kind of really rapid development and show the value of Spark to my organization. A lot of my organization doesn't know what Spark is. And you have to go through the motions and be like, no, you don't understand. Like this is actually a really useful tool as soon as you can start using it in real life applications. And so these are kind of subcategories, but whatever your domain is, I use the words analytical context, prediction goals, model selection, whatever you're doing, it's some analysis. You need to define kind of what you're doing. So the primary modeling unit is a term that I like to use and some other people like to use, but you need to figure out what level that's at. In my distributed energy resources example, that's at like a cluster site level. It needed to be at the site in order for me to simulate the impact based on structural assumptions about the house. And whatever framework you choose has got to be able to scale. If you're going to do things at the bottom level, if you're actually going to try to understand behavior at a bottom level, you need to have something that scales. And like I've said now multiple times, Spark is where I found out. So the future, I mean, because I've started to use Spark, I've actually gotten a lot of requests for help on stuff. One of the coolest things I'm doing is I have a client in the Middle East where they're trying to figure out their water issue. They have no water. And so we're putting water meters on all of their homes, trying to figure out what people are doing. We're talking about a country that has a population upwards of 40 million people, and they have no idea about their electricity behavior or their water consumption. And so this extends a little bit further than just the energy industry. It goes to any fuel that you demand, right? So I wrote natural gas. A lot of the heating in New England is all natural gas, and when there's an issue with the supply line, there's no heat in New England during a blizzard. These are sorts of things that are real life issues that we should be dealing with. And one of the coolest things, I just wanted to say this, one of the coolest things I've been involved with is my company, I didn't develop this at all. I actually know very little about the model itself, but there's this thing called the Baytown Systems Dynamics model, and it's really cool. It's using Spark now, but what it does, it's a climate change modeling simulation that's getting a lot of attention in the system dynamics literature. It's able to model, ironically, San Francisco, where I'm from, it's able to model the effect of climate change on the entire Bay Area. So it has like these different scenarios that say like a 1 foot sea level rise causes this much economic damage. It can geospatially locate where that's going to happen. And it's using Spark. And I think some of that is like the future. And that's really cool stuff to be able to use Spark on that. And then obviously what I'm primarily focused on, the last thing, is a holistic approach to our electricity grid. Like it shouldn't be a power plant produces the electricity, it goes to a company, you pay that company to deliver it to you, and then it's this long chain of events. It should be like more of a holistic approach, and that's where we're going to with the smart grid, where you might actually have a generator right next to your house that's powering your house. And in order to account for that, we need to have a better understanding of, well, the data that comes out of that. So that's something I see as Spark. Spark has a good presence there, and I hope that maintains. So with that, I'm done with 1 minute and 40 seconds left. That was good timing. And yeah, let me know if you have any questions. Thanks. I can hear you even if it's not on. What?
So your data acquisition, are you using A67 EDI files, or are you using Blue Button XML files for your data acquisition for your load?
Well, that is a loaded question. There is no yes, I'm using this, no, I'm not using that. It's because we're a consulting company, we do things on a project by project basis, and every client stores their data in a completely different way. Sometimes I get Excel files with 1,000 tabs in them, and I have to extract data out of that. The smarter clients give me like JSON or even CSV files, or they give me access to a SQL database or some sort of data warehouse. And there's different data sets that are coming in there, right? There's weather data that's stored in one particular way. There's, it's To me, that's what data science means. It's like understanding how these things are supposed to interact with each other and then modeling them in a useful way. So, sorry, I didn't really answer your question, but.
Yeah, very interesting talk. I'm just wondering, after you figure out how to predict users' behavior, what do you do about it? Why is that useful?
Well, there's Skynet. There's the danger of Skynet, right? Where they, Big Brother and all that kind of stuff. I mean, there's useful applications. That's the thing. And the one that I always come back to is, the world is changing really quickly, pretty obviously. And we've got disruptive technologies that are beginning to play a role in our lives. And just being able to predict and understand those sorts of things as they come about is what I think is the most useful knowledge of being able to predict people's demand. And a really good example of that, I have a colleague, Fred Coito, who taught me something really important. He's a forecaster. He used to work for a utility company, and he was doing the forecast for the whole company, long-term forecast, and he didn't actually, his forecast didn't account for the fact that the personal computer was going to be a big deal. And so it was just completely wrong, because now everybody has 6 computers, and the amount of energy that we all draw from computers is a lot. So that's the good example of like, well, knowing how people behave will help us to account for things that don't exist yet. Storage and... Oh yeah, I mean that's like a regulator question. Like, does it affect the pricing? And time of use rates, yeah, how they design those rates, understanding how people behave. That's exactly. Are you in the utility industry? Do you know? Yeah. Smart man.
Are you pulling any price information, LMPs from different ISOs or anything like that?
Oh man, you are in the industry. You know, you know what I'm talking about. No, so I mean, yeah, we do a little bit of forecasting for ISO New England, and understanding how the price affects the demand is a big deal. A lot of times, load forecasting applications don't actually use price, though. Oddly enough, it's actually not really a good indicator for. At certain levels, it's not a good indicator of demand. Quick example, like the price. Like I said, I have a client in the Middle East. There is no price of electricity. It's free. It's subsidized by the government. So, you thank God it's not really a good predictor because it doesn't exist. So I don't know. So sometimes, but not really. Not in this application. Okay. Cool.
Right. Please join me in thanking our speaker. Thank you.
All right. Thanks.